Okay, so what have we done? Actually, yes. So I've changed my mind. I will tell you approximately how this is proved. Okay, so proof sketch. Okay, or at least I'll reduce it to a certain question about Hom spaces. Okay, so step one is that there exists a homomorphism from the Heck algebra of W to the Grothendieck group of Bots of, well, so you should never talk about the Grothendieck group of a category unless it's Karoubian. So the Grothendieck group of the Karoubian envelope of Bot-Samuelson binomial. Do people know what Karoubian envelopes are? Because if not, I can go into it a little more. I'll do it in a second. Yes, but what does that mean? Right. Anyway, I'll go into it in a second. So the point is, there exists a homomorphism sending HS to the class of BS, and why? Right. Well, we've shown that BS is isomorphic to BS1 plus BS minus 1. So that implies that the quadratic relation holds. And we've shown that BS times BTS dot is B. We've shown all the quadratic stuff, right? STS plus so K plus 1, K minus 1, with, I suppose, the case K equals 1 being this. So we've shown these facts, okay, which imply the quadratic, the braid relation analog that we discussed. Okay, so relations hold in the right-hand side, and therefore the map is well defined. Okay, so you don't need this map to be an isomorphism to talk about the Hom formula. Okay, so Homs in BS-BIM induce a pairing on the Heck algebra. Okay, where the symbol of B paired with the symbol of B prime is the graded rank of the Hom space from B to B prime as, say, a right R module. Now, I haven't even assumed that these maps are free as right R modules, okay? But in fact they are. But I'm not even assuming it. The graded rank is still well defined. Okay? And this could be the zero pairing, right? For all we know, the right-hand category is 0, and this is the morphism from the Heck algebra to the 0. But it still defines a pairing on the Heck algebra. Okay? That's the crucial fact. And this pairing satisfies that HS is self-biadjoint. Yes. And whatever it is, this pairing is self-biadjoint. Okay? So this is going to be a pairing very like the standard pairing. And in fact, that means that Hom spaces are actually determined by Hom spaces to the identity, to the monoidal identity. So remember that pairings for which HS is self-biadjoint are the same thing as trace maps, right? The pairing was determined by epsilon and omega. Omega is just this self-biadjunction thing, and epsilon is the actual thing that determines it. So in certain types, you can reduce to certain Hom spaces. Okay? So the point is, if you know the Hom space from, say, a Bot-Samuelson bimodule to the monoidal identity, to R, then If you know all those Helm spaces and you know how big they are, then you know all Helm spaces and how big they are by adjunction, right? And in fact, in type A, you don't need to just do all Bot-Samuelsons to the identity. You could do all non-repeating Bot-Samuelsons, where no color is repeated twice. Why? Because trace maps on the Hecke algebra are determined by their evaluations on these kind of elements. So by a classification of trace maps on the Hecke algebra, you can actually reduce the number of calculations you have to do. So I'm not going to use that argument in the proof today. But this is an argument that I used in type A and in the dihedral cube case to make my life easier. Okay, this is an argument that you can use and is often used. So classifying trace maps on the Hecke algebra helps you reduce to only calculating certain maps. But I'm not going to use this argument. I was just sort of pointing out that it exists. But the point is that at this point, if yes, exactly. That's right. That's exactly right. So maybe I'll call this B as BIM. This pairing is associated to this category, to this potential categorification. Okay? So if the pairing associated to B as BIM is equal to the standard pairing, then we're done. Okay? First off, this map must be injective because the standard pairing is non-degenerate. Okay? So nothing goes to 0. I suppose the fact that the map is surjective is a different question. Right? We know how big this thing is. How do you know that there's exactly W item codes? How do you know that there's a right number of item codes? Well, that's actually also an argument you can make with this. Or you could call this an extra argument. That if we know at least the form of that there's only one idempotent associated with each reduced expression, then that's another argument. So, roughly speaking, we're done. Depending on the situation, maybe you need an argument. With some sort of upper triangle, with stating that there aren't too many indecomposed moves. Which is also a morphism theoretic style of argument. So essentially what we're trying to say is if we can show that the morphisms have the right size, then we have the categorification and the Helm formula. Okay, a Helm formula is really the important thing. Okay? And that this Helm formula can be checked on particularly easy things. So now what we're going to do is define a basis, and then one has to prove that this is a basis. Okay? Proving something as a basis is, of course, done via two parts, showing that it spans and showing that it's linearly independent. And these are both independent arguments. So for instance, in type A, I reduced to certain very easy Helm spaces, where I could use diagrammatic arguments to show that this particular morphisms span. And then the fact that the functor sends this, sends this into R or something. It's like you showed that any closed diagram reduces to a polynomial. Then the functor sends a polynomial to multiplication by a polynomial. This is obviously injective. In other words, you can't have a free rank 1 module. You can't have a module generated by a single thing get mapped to a free rank 1 module in any way other than injectively. If there's actually a map, right, then, or the left-hand side is entirely 0. But no, but I mean, like, even so, actually, no, it's not, the left-hand side is not 0. You actually have this map, you have a well-defined functor, and it hits multiplication by f. So it is surjective. So in fact, it must also be injective. Like, you know that certain maps are hit by this, right? You know that multiplication by a polynomial is in the image. So this left-hand side isn't 0. It just might be too small. It's not. Okay. But in this set of arguments, we're just going to show explicitly that we have a basis and that has the right size. So this is the next thing we're going to do. is finding bases for Hom spaces. So this is the whole White-Leaves business. I know you guys already are familiar with, but we'll do it anyway. All right, so the Zergel-Hom formula, so it's White-Leaves time. And White-Leaves, this concept was due to Lebedinsky. Nico Lebedinsky, a Chilean mathematician. Very fun guy, very sexy. He's Chilean. Chilean, yes. So, according to the Zergel-Hom formula, the rank has a right R module of Hom from this arbitrary expression to this other arbitrary expression is the pairing of this product of generators, this product of generators. And each side is written in terms of the defect formula. So this is the sum over x and w of the sum over reduced expressions for which they're expressions for x of v to the defect times hx. And then the same exact thing, let's say f inside y, v to the defect of f, hx. Okay? And remember that the h's are an orthonormal basis inside for this pairing, for the standard pairing. For this the Zergel-Hom formula. Are you objecting to the fact that I'm certainly this is the intended rank? Okay, maybe I haven't proven it's the rank yet, but I'm saying this is certainly what we will want. Okay, so this is what should be the case. Anyway, so the pairing of these two things only pairs the x terms against the x terms. Okay, so this is just the sum over x and w, sum over E and W and F and Y that both express x of V to the defect of E plus defect of F times 1. So in particular, we should be able to find a basis indexed by E's and W and F's and Y that give expressions for the same element. And that also motivates why maybe our bases should be split in half. That there should be something associated to E and W, something associated to F and Y, and then these will be glued together to form this basis. So this is what's actually going to happen. So we want a basis parameterized by a sub-expression of W and a sub-expression of Y for the same element. So we'll construct, so right now, choose and fix, an arbitrary reduced expression for x underline for every element. I don't care what expression you choose. Okay? And we're going to define and construct this thing, which I'm going to draw as a trapezoid. The light leaf from W to E, whose bottom is going to be W, and whose top is going to be our chosen reduced expression for x. It's going to be some morphism that we already know how to do. We're going to construct such a thing. Now, this construction will not be canonical. Okay? This construction is not canonical. So, if we really wanted to make it canonical, we wouldn't just fix this data. We'd fix even more data. It depends on a choice of Rex moves, on choices of Rex moves. So actually, if we really wanted to make it canonical, then for every element and every pair of reduced expressions, we would choose a path between them. And in fact, for every element and every simple reflection in its descent set, we choose a reduced expression ending in that element. So we do a lot of things, but it's not so important. It's just any of these things we'll call a light leaf map. Okay. So before we actually do this, we're going to do some examples. Okay, so let's say MST is 3. Okay, let's do STS. And let's do 0, 0, 1. So we're at the identity, so this first 0 is an up. The second 0 is an up. And this third 0 is an up. And the final target is S, and there's only one reduced expression. So it should go like this. It should somehow fit in here. And what should the degree be? It should be +1, +1, so it should be degree 2. And we do this inductively, okay? So first we define the map associated to GS, this, which should be some degree 1 map from S to the identity. So in fact, it's just going to be a dot. Then, and you know that the target after that point has where we got after that point. Then we do it again. We're at the identity. We're doing T, 0, up 0 again. Do that. Now we're at the identity. We do up 1. We need to get there. We need a map of degree 0. Well, it's just the identity. Okay? So we've actually seen that up 0s are actually just dots. And up 1s are just identity maps. Let's do another example. Okay, here's the other reduced expression for S. But this time we go up, and then this would be an up, but we don't take it. And then this would be a down, but we don't take it. Okay? So the first thing we do is get from the identity to S, and we actually do it. So we just go up. There's the identity map. Now, we need a map from S to ST of degree 1. Well, we just shouldn't take this. This is an up 0. We should just put a dot there. So now, after 2 steps, we're supposed to end up at S, and that's where we've ended up. And then we're supposed to go down. Okay, well, we're not actually supposed to go down. This is supposed to be something in degree -1. Okay, so we're at S. We're adding a new S, but we're not doing it. We might as well fuse them into 1. That's a way of not actually letting the S effect in. Okay, so the conclusion is still S. This has the right degree. So down 0 is a trivalent vertex. Whereas if instead we'd done down 1, then we'd start in the same way. But now we would take the S, which means we have to get rid of the earlier S. So we cup it off, and our target is now the identity. Okay, so we've seen the 4 possibilities. Up 0 is a dot. Up 1 is just a straight line. Down 0 is a trivalent. Down 1 is a cap. However, it's not quite so easy, as many of you already know, perhaps. Let's do STST. Up, up, up. 1, 1, 1, 1. So in fact, the first 3 ones are ups, but then this is equal to TST, so this is actually a down. Which means that in the first 3 stages, we just do the identity. What color is it? Yeah, this goes to ST. This goes to TS, sorry. So we do the identity, identity, identity. This is the first thing we do. And then we're supposed to put a cap. Okay, because T brings us down, so we need the T to cancel something else out. But, you know, we can't just immediately draw a cap here, because this guy doesn't have T on the right, and we need to get it past the S. So what we do is we apply a reduced expression. We change our reduced expression to a reduced expression that has T on the right-hand side. And the way we change reduced expressions is applying a Rexman. Now we have T on the right. So now we can just do our normal thing. And the result is TS. Okay. So we had up 1, up 1, up 1, so we just did the identity. Okay? Now we have a down 1. So in order to apply our cap, we need something to have the cap attached to. So we need t to show up on the right of this expression. We know t can show up on the right of the expression because it's in the descent set, otherwise this wouldn't be a down. So apply some rex move until you get t on the right, and then apply the cap. Now, there's a choice here. Which rex move do you do? In this case, there's really only one. I guess you could have done this, and then that, and then this, and then that. You could have applied this MST valent vertex an odd number of times, but 3 times is equal to 1 time. So it doesn't matter in this example, but it does matter in other examples. I'll give you another example. STS 111. Okay? Here is just up, 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 right? Okay? So this identity map is a valid light leaf. Here is another valid light leaf. Okay? There's no reason to do this one, but it's totally acceptable. For no reason at all, I decide to apply a rex move. Why not? Okay? So basically, I'll get to the form of this in a sec, but you're allowed to apply rex moves whenever you want. Okay? Let me do one more example. STS up 11100. So again, this is just up, up, up until the longest element, and these are both down. So here we are, we're at the longest element. Okay? We need a down 0, which means you need a trivalent vertex, which means we need t on the right. So we apply a reduced expression to get t on the right. Apply a rex move to get t. The target is still, it's just STS. But yeah, forget what the target is. You should just build it up progressively, and you'll see what the target is. You don't need to think about it beforehand. You'll get there. So we get t to the right, and then we bring it down, which means that we apply a trivalent vertex. And now we're still at STS as we should be, right? Because this is an expression for STS. And then we have an S again, and we need it to go down. So we need to apply a reduced expression move to get S on the right again. And then we can apply the trivalent. And if we wanted to, we could apply another braid relation up top, if we really wanted to. Okay? So the inductive rule is this. Right? We've done I steps. So here's the first I terms. Here's xi. So we've made it to some reduced expression for whatever the first I terms give you a reduced expression, or give you an expression for. We've done the first part. Okay? And then what happens next, there's 4 choices for what happens next. Okay? If it's up 1, okay, then we do it. Now we end up with a reduced expression for what we want, but we can also apply some rex move. Okay, and then we end up with our chosen, forget choosing something, I don't really care. You can choose it or not choose it. You can fix it beforehand. You can do whatever you want. Okay? So basically, up 1 is a straight line, but you're always allowed to do some rex moves. So similarly, up 0 is this. Yes, just combinations of those. And similarly, for an up 0, you can do this. And if you really wanted to, even though you're not even changing what you're doing, you could apply a rex move. I don't care. And then for down 0, well, so now you definitely you may need to apply a rex move in order to get the thing that you want on the right. And then you could apply another one if you wanted to. And down 1 is the same way. Yeah, so if you want to make this canonical, rex, then this caps off. So if you want to make this canonical, if you want to fix a reduced expression, then this may be necessary. Absolutely. But this is the inductive procedure, and clearly, if you really want to make a canonical, you need to make your choices of all the Rex moves you could possibly make beforehand, and all the intermediate reduced expressions. But, you know, in general, well defined up to a choice. And then, given this, we have E inside W, we have F inside Y, with them expressing the same element. In that case, the double leaf associated to this pair is going to be a map from W to Y. And we do it by first getting to our reduced expression for X. Here's where it really matters that you chose the same reduced expression. Because then we go upside down, do the upside down version associated to Y. That's just the exact same thing upside down. Although again, if you decided to not have the same reduced expression in the middle, then you just do a Rex move to get between what you chose here. So it doesn't, it really doesn't matter. Exactly. So this is the duality functor, which I haven't yet discussed, and for which there will be exercises. Yes, flip it upside down. Okay. So this is all well defined up to a choice of Rex moves. And the theorem is that these things, double leaves, form a basis for from W to Y. So I'm going to stop writing the BS of this, BS of that. You know, maybe we're just in the diagrammatic category. As a right R modulo. So I mean, this is important. Taking one of these things and multiplying on the left by a polynomial gives you a map, but you can then pull that polynomial across and somehow get it on the right side, and the corresponding terms that you'll get in between are also going to be linear combinations of these things. Doing that is, in practice, is pretty hard. Okay, so a lot of practice, a lot of exercises are needed to actually work with this. This is not the best basis in the world, okay? Okay. Yes. Oh, R is still, I mean, the diagrammatic category is defined in terms of a polynomial ring. You start with a polynomial ring, and then you define the diagrammatic category. Because you need to know what you can put in a box. I mean, you need to have an action of, because, I mean, one of the relations is, you know, right? So you need to know what this action of W is. The diagrammatic category, one of the inputs is, the input is precisely W acting on a ring, as well as a choice of simple roots. We're not assuming the objects are bimodules, but there is a ring that's floating around. And yes, I'm not assuming that the ring R acts on it freely. All right, certainly, yeah. No. Yeah, start with the realization, then you can define this diagrammatic category. And then this will be true. Yeah, right or left. Yeah. I've been choosing right, exactly. But certainly not both at the same time. So let's just discuss some consequences. So clearly, of course, showing this will show that the Hams have the right size, and that will finish our proof. We'll also show this fact about, I'll get there in a second. So the first consequence modulo, yeah, this theorem is used to prove the previous theorem. So, but I be an ideal, so here's the first consequence. I be an ideal in the Brouillard order. Right? In other words, if V is an I and W is less than or equal to V, then W is an in other words, all things less than or equal to x are an ideal. So let di be morphisms factoring through a reduced expression for v for some v in this ideal. But this is also the same thing as the span in any given Hom space of those double leaves which factor in the middle through some element in the ideal. That's not very hard to show. Okay. So here you've got this, you know, for this is an ideal in V. Right. So what is an ideal in a category? It's a subset of every Hom space closed under any sort of composition, monoidal or not monoidal, just vertical composition. Okay. So when W is understood, D less than W, all the things that factor through reduced expressions for elements less than W, is called lower terms. Right, so for instance, suppose we're discussing Rex moves in the reduced expression graph for W. Then W is, we know what W, we know what W we're talking about. When W is fixed. Lower terms are always with respect to a given lower terms with respect to W is what that is. Okay, so now I can make very clear the point. So W and W prime are reduced expressions for the same element. And beta prime are two reduced expression moves. You know, so they're both maps from W to W prime built up out of these things. Then B minus B prime is in D less. This is this claim that I was making before. But how do you prove this? Well, we know what all the monodromy is in reduced expression graphs. And we've given relations that explicitly say that for every generator in the monodromy, this is true. And that implies it's fact. Okay, so this is just a consequence of the relations. Okay, okay. So suppose that I have got two paths from here to here. Okay? And to get from this path to this path, there's a sequence of transformations, like go across a disjoint square, and then go across the A3 relation, and then go across this other relation. Okay? So each of these changes we can apply locally. And you know, locally, the relation that lets us go across that cycle, so the difference between these two Rex moves is in lower terms. Okay? But then we're doing that locally, and then we're composing it with the rest of the Rex move. Okay? But this is an ideal. So even when we compose it with the rest of the Rex move, then it's still within this. Okay? Then we repeat. Okay? So we do this for every single transformation until we've transformed one Rex move into the other Rex move. And at every successive step, the difference was in this ideal, so the sum of these differences is in the ideal. Yeah, one can do this in practice. No. The point is that the monodromy is generated by these kind of cycles. But this is true for any Coxeter group, any element. Yes, this is. Yeah, that's a fact that you need to prove this. Absolutely. That was something that I discussed last in the fact is proven, this is a standard fact from, Coxeter complex topology. Okay. And the implication of this, of course, is that, these LL maps that we're using to define everything, but again, are not canonical, right? Because they depend on a choice of reduced expression maps. But they are well defined modulo lower terms. Modulo lower terms. Well, modulo, so this is, with respect to where you're going. So that's consequence 2. Consequence 3 is similar. So if you have a reduced expression, right, then its endomorphism ring is spanned by these light leaves. And there's only one sub-expression for W, and that's 1, 1, 1, 1, 1, 1, 1, 1, 1, all ups. Okay, and the corresponding light leaf map is the identity, or some Rex map. And then similarly, the other half, going from upside down, is the same thing. So in particular, that this thing is the identity, it's certainly plus lower terms. That, the identity is obviously an element in here. It spans a one-dimensional space, and everything else is lower terms. And here's an important consequence of this. Okay? So that says that there exists a unique, indecomposable, or maybe primitive, depending on your favorite language, idempotent in this endomorphism ring. Let's call this idempotent E, such that E is equal to the identity modulo lower terms. Okay, if you have two of them, then when you take their product, you're just multiplying one by one modulo lower terms, so they can't be orthogonal. So that's why you. So they must commute with each other. Oh, sorry. And they certainly commute with each other modulo lower terms, but you don't know immediately that they commute with each other. But this is sort of a standard thing that you show in this is a standard algebra play. This lower terms forms an ideal, which is clearly contained in the maximal ideal. You can do some Jacobson radical stuff to argue that there's some sort of idempotent listing. But if you have anything which is an idempotent modulo lower terms, it can be extended to an idempotent. You can use that to make all sorts of arguments. There's some exercises that are very similar to this. Okay? But this gives you the classification of indecomposables business that I was saying before. Okay? That if you have this reduced expression, it has sort of a specified important idempotent. Okay? And that if you have two different reduced expressions, then this Rex move between them, okay, acts as the identity on this part. Right? It's the identity, it sends the identity map on one to the identity map on the other modulo lower terms, and if you come back, So this thing sort of gives you an isomorphism between the image of this idempotent and the image of that idempotent. So, everything can be proven modulo lower terms is the point about this. So there's, this plus some algebra gives a classification of indecomposables in B. And this algebra is on the exercise sheet. It's also pretty well done, I think, in my paper with Jordan. It's well explained. So it's worth reading that. And the fourth consequence, which really is sort of some more general notion of all this stuff, and sort of is the general context in which these kind of arguments can be applied, is that D is an object adapted such cellular category. Okay. So this, a cellular category, is something you'll find in the literature. Object adapted is my terminology for this sort of special case. I'll describe what it means now. You've already seen another object adapted cellular category, namely the temporal leaf category. Okay? And there's an exercise about unraveling this. But let me just say what this is. So this is a category equipped with a bunch of structure. Okay? So what structure? You have a subset of the objects. Okay? In this case, it's a fixed rex for each W and W. We have a partial order on this thing. So it's actually a poset. And in this case, it's the Brouillard order. We have an anti-involution on the category. I'm defining an object-adapted cellular category. So the only difference between this and an I'll explain the difference. Okay. So this is an anti-involution of the category. In other words, it's a functor from the category to itself, which reverses the composition order of bimodules. And you apply it twice, and you're right back where you started. So this is flipping diagrams upside down. It acts as the identity on objects, and on morphism it flips diagrams upside down. On the category. Yes, it's a contravariant function. It's a contravariant function whose square is actually the identity, not just isomorphic to the identity. Square is the identity. But it doesn't really matter. Isomorphic to the identity is good enough. Yeah, but really, you might as well just make it. Yes, it is. So there's still more data. Okay, so for each object, so an arbitrary object, and every special object, you have finite sets EX lambda and M lambda X. Okay? And these two objects are in bijection. These two sets are in bijection. So in the literature, you usually only see one of them, but I think that makes things more confusing. I think it's better to think that there's two of them in bijection. And this bijection I'm also going to denote with the letter I. Like maybe that should be iota and this should be I. if you can tell the difference between them. So in our example, E Wx is the set of expressions for W. Sorry, sub-expressions for X. And that's also what M is. But I'm really thinking about this as being a light leaf pointing up, and the M as being the light leaves upside down. Okay, so finally, we're almost done. And a morphism. So for all T in EX lambda and S in M lambda X, lambda Y, say, you have CT in HOM X lambda and CS in HOM lambda Y. So these are the light leaves. The upside down. Okay. Now we finally get to say what these things satisfy. Okay? Such that, so if we flip CS upside down, we get C of IS. drawn these. That's wonderful. The second condition is that we're going to let CST lambda, this notation is unfortunate, but this is sort of the way it is, be CS composed with CT. Okay, so if S is in here and T is in there, then this is actually a map from X to Y. Okay, so this is XY. And the collection of all these things, CST lambda for various lambda, and various T and EXY, X lambda, and various S and M lambda Y, the collection of these things is a basis for this Hom space. Okay, so this is the double Leaves basis. And then there's the most important property. So far we've sort of talked about categories where a basis of more, you can find a basis that's split in half. You have something composed of this upside down. But now you need some sort of property which makes, which gives you this ideal, which gives you this lower terms thing, which is the really useful thing we were using earlier. And here's that final property. So if A is an arbitrary morphism, let's just say it's in Hom, Y, Z, some arbitrary thing. Actually, sorry. So it's CS goes from lambda to Y. Good. And S is in M lambda Y. Then, if we take CS and compose it by A. Okay, so what are we doing? We're taking this upside down light leaf, and we're putting some arbitrary thing on top. Or maybe we can apply the involution and take a normal light leaf and put an arbitrary thing on bottom. Okay, so what do we get? Okay, think about what happens here. Okay, we do some arbitrary stuff on the bottom of the diagram, and it's a linear combination of things. So two things can happen. One is that the result still doesn't factor through any shorter terms. In which case, it should be sort of expressible as light leaves going to this guy. And the second is that the result, so maybe a dot from A pulls all the way up to the top. And so it must factor through lower terms. Okay? So the point is that when you multiply these things, this is supposed to be some linear combination of CS primes. So the coefficient is called LASS prime, so some coefficient, some arbitrary coefficient depending on A and S. So some linear combination, okay, plus lower terms. And what I mean by lower terms is the span of these C lambda STs for C mu ST for mu less than lambda. Okay, and so this condition, one thing it does is imply that everything less than or equal to lambda is an ideal. Because you can compose by anything and it's still in this ideal. Okay? So I mean, what's the consequence of this? The consequence is that if you take A and you multiply it by CST, right? This is A times CS times CT. Yeah, so this is inside Hom from lambda to Z. Okay? So S prime is actually in M lambda Z. Thank you for interrupting. That's going a little too fast. Okay? Because we've changed the target of our map. Okay? But of course, this thing is itself a Hom space and other thing, so it has this basis. Okay? So it's weird because we're mixing sort of like single things with double things. But this still makes sense. It does make absolute sense. But so let's just look at the consequence because that'll make it make sense. Okay? So we multiply A by one of these basis elements, by a double leaf. The definition is now complete. Okay? So here's the picture that I want you to have now. this is factoring through lambda. Okay? So two things can happen when we multiply A by this guy, right? We either turn it into a big thing with the same thing on the bottom unchanged. Okay, so here's S, here's T, here's S prime T, the linear combinations of these. And then we some crazy map factoring through some lower term. Okay, so this is some mu less than lambda. Okay, so this is not a Lightweight map. This is just some arbitrary thing. Okay, but this arbitrary thing can then be refactored in terms of the Lightweight basis as something that goes down to mu and then back up and then applies LLT. So these are some other random LLs. Okay, but then this can be refactored, and this can be repeat until eventually it's in the right form. But regardless of what it does, it's going to end up being less than mu. Okay, so this sort of lower term stuff will screw up, and what lower terms you get will depend on LLT. Because this thing will have to suck into this thing, and you'll have to sort of like repeat some sort of argument to turn this into the right form. But this thing right here is already CS prime T. Okay? Because this never stopped being lambda. Okay? So you never actually had to go down to lower stuff. So this is the sum of, you know, L, A, S, S prime, C, S prime T plus lower terms. And these coefficients do not depend on T. So if you replace this Lightweight map with some other Lightweight map, you get the same exact coefficients. Okay, because all that's happening is that A is screwing around the top, and nothing's happening. Like these things are just kind of going straight up, and no dots are going into them that could be sucked into the lower term. So nothing is happening to this part here, which means the stuff below is unchanged. Okay. Whereas if you screw up, then you might have a dot going into the bottom, and that gets pulled into the T, and that makes everything complicated. And then it really did matter. These lower terms do depend on T, but these coefficients do not. Okay? These depend on T. Right. So an example of a cellular category or a cellular algebra, which is a category with one cell, is a matrix algebra. Okay? And you should think that if you take a matrix and multiply by EIJ, so this, you know, like the one in this particular term, okay? Then what you end up with is a certain column of your matrix, okay? So the elements in that column are these coefficients, okay? And if you changed, you know, which EIJ you're multiplying by, so long as you're staying within the same row, I forget which row column, that doesn't change which column you care about. It just cares about where you put the column in the end. So when you multiply this, you get the column in the same, you get that column put in the same column. Okay, if you shift which row you're in, if you shift which column you're in but stay in the same row, you get that same column put in a different place, but the coefficients are still the same. Okay, so you change T, but you haven't changed the coefficient. Whereas if you change which row you're in, then that's a totally different thing. Okay, then you're changing the coefficients. There's no lower terms, so you don't have to think about that. So that's an example. You should think about why the EIJ basis of matrices on a cellular basis. This is really the cellular condition. This is the important thing. Yes. Yeah. Okay, so first off, a cellular algebra is a cellular. So here's the thing. Okay, now I have to give you the difference between object adapted and non-object adapted. Right? So you know, in the literature, just an ordinary cellular category is defined in basically the exact same way. the difference is that instead of having CST lambda be defined as, as a composition of two halves, okay, this is not the case. Okay, this is no longer the case. You just part of your data, CST, this basis is the data. So instead of the two halves, CS and CT being the data, you actually just have this thing be the data. So lambda, and so the first difference is that lambda is just a poset. In other words, there's no identification of it with objects. It's just some arbitrary abstract poset. Okay, so like for instance, for the Hecke algebra in type A, the poset is partitions, which clearly has nothing to do with any objects, because there's only one object in an algebra. So it's just a poset. Okay, some arbitrary thing, which means that we can't even think about this as a composition of two things. All we can do is define elements. Okay, and then what they satisfy is this. Satisfy this. And I suppose the other thing they satisfy is that, you know, interpolating this into a condition of a basis, I of CST lambda is C IT IS. Okay, so that is the corresponding way to define it. So in this case, you're sort of forgetting that each thing factored as 2 points. However, it's as if it factors 2 points. Okay? When it actually does factor, it makes life a lot easier. Okay? But for the Hecke algebra in type A, it doesn't. It's not like there's some objects floating around and you can have it factor through. Yeah, a Kazan-Lucy basis element is not necessarily a product of two things. It's really, you know, so there's no way to generalize this. This whole object adapted to the category is something that is really much more useful for these kind of categories, for expressions of monoidal with one object, yes. So there's only one Helm space that you care about. So it's an algebra with a basis, CST lambda, and an anti-involution II satisfying some properties. The most important one being this property here, which if you ignore this middle part, is just a statement about the CST lambdas. Yes, that's correct. Their categorification is. That's correct. And by the way, objects of adapted cellular categories are not closed under equivalence. Karoubi envelopes of object adapted cellular categories are not object adapted cellular categories. Or maybe Karoubi envelopes are, but equivalence is not good enough. So, like, this specifically, you know, it's specifically because I chose a nice thing. So I guess Karoubi envelopes are, but yeah, having you factor through intermediate objects is a nice feature. And this won't work if I just chose, you know, if I chose a category where the objects were sort of indecomposable Zergo-Bime objects and looked at all morphisms between them, it'd be very hard to describe these things. Wouldn't really exist. So. No, and this has nothing to do with the cellularity on the decategorified level. Okay, so cellularity on the decategorified level is something to do with categorification. It's a very different story. This is this thing that you have to read Mazurchuk and Mimietz to understand. Mazurchuk and Mimietz have this long story where they talk about what it means to categorify a cellular algorithm. And that's a totally different thing, right? So remember, the downstairs, yeah, in abstract, but not exists. Well, for the Hecke algebra type A, they're just using Zergo-Bime. For Hecke algebras, they're just using zirkel bimodules, but they're describing general features of categorification of cellular algebra. They're not saying that we can categorify any cellular algebra. They're saying if you have a categorification of a cellular algebra, what properties do you have? So this is not something you should think is particularly, this is something totally different. You know, downstairs in the Hecke algebra, the anti-involution is this bar, is this not bar involution, but this, yes, it's omega. Is the anti-involution downstairs in the Hecke algebra. That corresponds to the cellular structure. Omega is categorified by the biadjunction, the functor of taking something to its biadjoint, which has nothing to do with flipping a diagram upside down. It has a lot more actually to do with rotating a diagram by 180 degrees. Okay, these are just very different things. They're not related to each other. You should completely ignore the fact that the Hecke algebra is a cellular algebra. You should think, you know, this is, we're really talking about something very different. And it's an important confusion. So there's an exercise that walks you through the proof that indecomposables in an object-adapted cellular category are classified by length. So. An object-adapted cellular category, the indecomposables in the Karoubi envelope are classified by. So this is basically the argument that I only sketched here. Okay? And I think in the exercises it doesn't really do it in this generality, but it's the exact same argument. It really works. So this is just a general thing. It's a very general thing. It shows up in other contexts as well, but people don't usually try to talk about it in this generality, which is annoying. But also the notion of a local intersection form is also something that's totally general for an arbitrary object. People who are used to temporal loop algebra talk about intersection. And yeah, why don't I talk about the intersection form? Because it will open up a lot of exercises. So the exercises on the sheet today have both exercises on the local intersection form and the global intersection form. But maybe for time I'll just do the local intersection. So what we're going to do is we're going to fix an arbitrary expression and an element in W. And K begin being equal to 0. So consider the following pairing. So we've got sub-expressions in W for X with the defect being K. We think of to these things we associate this white leaf map of degree K. And then we compare this with the same thing, except that the defect is minus K. And that will give us a map back. And when we compose these two things, well, if we compose them in one direction, we get an endomorphism of W. Okay, but if we compose them in the other direction, we get an endomorphism of X. Okay? So then these compose to the endomorphism ring of X. Okay? In degree 0. But remember that the endomorphism ring of X, when you mod out by lower terms, is just the identity. It's just one-dimensional, R, given by the coefficient of the identity. Right? So when we take this thing and we write it and rewrite it in terms of light waves composed in the normal order, from x to things lower than x, then we have the identity map, and then we have even smaller terms. That's correct. Yes. So you know, here's a standard point. When you have a cellular algebra, it's easy to do a change of basis and get another cellular algebra structure on the same line. Right? What you do is you take CS or maybe CST and add to it some lower terms. You'll get a new cellular basis. Right? Clearly, this, you know, the actual specific properties of this thing only cared about, you know, didn't care modulo lower terms. I suppose you should, you know, make it so that the involution preserves this. So the lower terms you add to one thing, you should add to the upside down thing as well. Okay. But you can always shuffle around, add some lower terms to get a different cellular basis. So, you know, for any choice, just once and for all, fix a choice of each light wave. Any choice, I don't care. You'll get a cellular basis. And you can use. This is the identity plus the lower terms. There's some coefficient of the identity. And this coefficient is what we care about. Okay. So let's do some examples. So what's the point of this thing? Well, I'll get to the point in a second. First, I'll do this. K is also fixed. Here's an example. So let W be the sequence STS and X be S. This is M. M is arbitrary, and M is bigger than or equal to 3. K is 0. Okay. Then there's only one thing. Each of these is a one-point thing. Okay, so this light wave here, colors. This guy is the only guy. Okay? And so this pairing says, take this guy, and then the upside down version of this guy. Well, what is this? This is equal to this times alpha st. And so this is the coefficient we care about. So it's a pairing that sends the unique element of each set, or the unique element of that set, to alpha st. Okay. And since n is bigger than or equal to 3, alpha st is not 0. Okay? Or I guess outside of defined church. So, you know, you can also take the vector space spanned by these things, compare them against each other, and that will give you a form on a vector space. So these two vector spaces are an obvious isomorphism. You could really think about these vector spaces as being naturally isomorphic, or rather, perhaps this intersective form, if it's not degenerate, gives you a natural isomorphism. It's not usually non-degenerate. This is the local intersection form on W at X of degree K, if you really want some sort of way to pronounce this out loud. Okay. What's the point of having such things? Okay. So suppose that S and T pair to 1, right? Which is to say, I've got some S here, T there, and this composition is the identity plus the lower terms. Or maybe some multiple of the identity, at which point I'll rescale one of these two maps. Okay. Then, composing them in the correct order, this thing here, this is an endomorphism of W. And it's almost an idempotent. Okay? So is almost an idempotent. Okay, so if we did it twice, then this part in the middle is just the identity plus things that factor through lower. Okay? So it's, and this is just a general, and this is the algebra argument I was saying, that if you have something which is almost an idempotent, then it can be, then you can adjust it by lower terms to get a true idempotent. Okay? So algebra, and this is kind of in the exercises, says that there exists an idempotent, which is equal to Ts plus lower terms. Okay? So really, you think of T as being projection, and S as being inclusion. And this isn't exactly true, but it is true modulo lower. Okay? So in fact, in D modulo D less than X, T is projection, S is inclusion. To sort of the indecomposable object Bx. Right? Which, you know, in this category doesn't depend on the reduced expression at all. Right? So it's a map not just to X underlined, but really to X, because the reduced expressions from natural isomorphisms between them, compatible isomorphisms between them. So all of these things are canonically identified in this equation. So maybe Bx is maybe, you know, Bx is equal to X. And so in particular, that implies that Bx for the shift by K is a summand of BSW. And then if you flip this upside down, it still pairs to the identity. So also, Bx of the shift by minus K is a summand. When K is 0, you don't want to include it twice. It only shows it once. When K is non-zero, both of these things show. Okay? And in particular, the rank of the local intersection form gives the multiplicity of Bxk as a sum. You choose a sub-basis which is orthonormal, then you can construct orthogonal. Or you can construct a family of almost idempotents which are orthogonal modulo lower terms, and use the same sort of arguments to complete them to true idempotents which are genuinely open. So this is, again, something that's very general. But that's sort of the math behind why computing these things is important. And do you want me to do an example? I don't know if did I put the type D example on the exercise sheet? I didn't even send you the exercise sheet. You have no way. Do you want me to do an example? So this may or may not be on the exercise sheet, but if it is on the exercise sheet, but, you know. Object adapted. Yes. Yes. So people who study the temporal algebra have already been doing this, right? In the temporal algebra, like, you know, you've got n dots, and your cells are just, you know, also natural numbers. and this, E and K is sort of cap diagram. So you're going down to, here's 4 dots, you're going down to 2 dots. And you take sort of all crossingless matchings you can, but where these two don't connect. Where there's sort of all of the full number of strands that go from bottom to top. Okay? So if you have an arbitrary, suppose you have some crazy arbitrary thing where 2 strands go from bottom to top, then you can cut the diagram in half, and it's a composition of something of a so-called cap diagram and a cup diagram. Okay? And then the pairing that you use, if you have a cap diagram, and you have a cup diagram, I guess this isn't endomorphism of n. This is map from n to m. These are different. So you can only pair it when they have the same number. So if you just come up with some arbitrary thing, okay, then you can compose them. You get an endomorphism of 2 strands. In this case, you get this. And you count the coefficient of the identity, which in this case is 0. Because fewer than 2 strands. Okay? But if I'd chosen some different thing, so for instance, that, then when I compose them, I get the identity. So the pairing between this diagram and that diagram is 1. So they compute these, and sometimes you end up with like extra circles and things. So I've done instead of this. Then the pairing is -2 or minus quantum 2 because this is a circle. So actually computing these intersection forms and their determinants and their ranks is difficult. There's no real closed forms for this matrix. Topology is hard. Okay, let me do an example which will justify. This is the easiest example. Yeah. So light leaves. All right. So when you color everything and turn it into circle diagrams, you mean? Oh. Right, so in this picture, crossingless matchings are light leaves. But, random linear combinations are also elements of this thing, right? The fact that we chose crossingless matchings wasn't arbitrary, it's that they're a nice basis. It's that they're cellular basis. But if we'd chosen some random thing. So, I mean, there's other bases, right? But remember that, like, in knot theory, people care about over and under crossings. So this is something like this plus q times that, I forget. Okay? And so I could have chosen braids to form a basis instead of crossingless matchings. Okay? But instead, that wouldn't be a cellular basis. So yeah, but the fact that I taught you the sample weave algebra the way I taught it to you makes it clear that yes, it's a nice. This is going to be that type D example. I personally watched some of you do. Okay, so the color I'm going to use the least is orange, or yellow. This guy in the middle is yellow. And the other 3 colors are our favorite 3 colors. I could. I won't. Even though that seems like it would make things easier. Okay? And we're going to let W be SUV T SUV. And X be X. So in the exercises you computed that there's 8 light loops. Okay? And so let's write down what they are. 8 light loops. Okay? All of them had 0 at the T stop. Okay? so, and we're going to write down their degrees. There's a unique one of minimal degree, and it had a 0 in the t-stop. It had 1s on the left and down 0s on the right. So this was this thing. Okay, so let's actually remember how this worked. Okay, you know, this is 1, 1, 1, 0, 0, 0, 0, up, 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 down, down, down. 6 degrees minus 2. So. Okay, so the first thing we do is 3 ups. Then we do an up 0. That part's fine. Then we do a down 0. So we need to apply a reduced expression to change this so that the red shows up on the right. And that's just a bunch of crosses. So maybe having drawn it this way is not exactly in this form. I do it in a slightly different form. But basically, you cross this line over, and then you do this cap. And then you cross the blue over, and then you do that, and you cross the green over, and you do that. So it's not exactly what I did, but I did something which is obviously equal. Okay. And then the other ones, so there were 3 of degree 0. And they were all sort of move one of these ones to become over there. Okay? Which means that, for instance, this is now an up 0, and that's an up 1. Whereas these behave just like before. Okay? Or I could have, instead of doing it with red, I could have done it with blue. Or I could have done it with green. Similarly, there's 3 in degree 2, where I do it with 2 of them. Etc. And then there's 1 in degree 4, where I did it with all 3. So now, what are the pairings? What are we pairing against each other? This is all 8. There's 3 here. 1, 3, 3. Okay. So we're pairing this 1-dimensional space against this 3-dimensional space. This 3-dimensional space against itself, and this 4-dimensional space against 0. Well, I'm just saying, what are the choices of k that are inputs, right? I mean, like, for k equals 4, you're pairing this against 0. So the rank is obviously 0. Or k equals 2, you're pairing a 3-dimensional space against a 1-dimensional space. So the rank is either 1 or 0. And for this thing, you're pairing a 3-dimensional space against itself. So the rank is something. Okay. So let's do this computation. Okay. So I mean, if we pair this thing against any one of those, I'll put this one upside down. And then we put another one on top, so maybe I'll do the blue one for simplicity. I think I switched the order of red and blue, but it really doesn't matter. Okay, so what do you get? Okay, so this dot pulls in. Okay, but we got this yellow thing, and we need to deal with it. I didn't do this right. We have to have 2 dots. Sorry, 2 dots. 2 dots. Because we're pairing this guy against something in this degree. So on top, we need to have 2 dots. That makes a lot of sense. The thing I drew earlier was 0. Okay? So what happens is that these two pull in, and this yellow dot only has to go through the green thing. It has to cross the blue one. Absolutely. It does have to cross the blue one. But what happens when we take a dot and we put it across a crossing? We get the Jones-Wenzel. The Jones-Wenzel in this case is the identity map, so it's easy to deduce that what you get is this. Just pulls it. And similarly, and I was using this without sort of saying it before, well, we split this in half, and then, okay, so a trivalent vertex also pulls it. So MST equals 2 is really easy. And I guess even the third thing that I was also using was the 3-color relation. That if you have a crossing between red and green, that this also pulls through. That's the 3-color relation for A1 crossing A1 crossing A1. So I was using all of these things subconsciously. But basically, distant colors, they ignore each other. Okay. So this thing pulls into there, this thing pulls into there, and what you're left with is you need to take this yellow guy out of the green. Okay? Which, you know, when you pull it through, it has 2 terms. One where I bring it to the outside and multiply and act by, you know, and act by V. And one where I break it and create the de Mezurac. Well, the term where I pull it out leaves this big green hole empty. And there's some other stuff, but when there's no yellow in the way, I can just pull it out. And I get an empty green loop and then 0. Okay? So I only care about the term where this breaks. So this is equal to, well, the red line now goes straight down. The blue line now goes straight down. The green line sort of went over or broke, but those pull through. So the green line's now that. And the coefficient that I get is dV of alpha s, which is -1. Because their MSD is 3. MSV is 3. So the pairing of this guy with him, him, and him, each of them is -1. Calculating is identical. Okay? And in particular, this form is rank 1. The 1-dimensional space against the 3-dimensional space. Okay. See what? Because of this. The yellow, oh, alpha T. Thank you, that might have been the confusion. I saw some looks that were confused. Okay. Now, if you do the computation of this guy paired against this guy, okay, what do you get? Well, that's basically the same thing. In that case, this guy was like this on top, but on bottom it looked like this. Okay? So this bottom half is the upside down version of him. Or I can switch the colors. I shouldn't have done that. I'm a bad person. The upside down version of him with the color switch. And the top is the upside down version of him. And so the calculation is still -1. However, when I pair this guy against himself, what do I get? That's a new calculation. I'll do the colors correctly this time. So here's the top, here's the bottom. So that's pairing him against himself. And you'll see that I've got an alpha T inside basically 2 separate loops. Okay? And if I pull him out of one of them, then that would contract and is 0. Okay? So if I break him out of this one, then now the blue loop contracts, and that's 0. I'm basically taking two De Mazur operators of a linear term. So, that has to kill it. Okay, so this is 0. Because I'm taking essentially taking du of dv of alpha t. But this is 0. Because it's for just degree reasons. So the matrix, the 3x3 matrix that you get here, it pairs any one of these guys against itself to be 0. And it pairs each of them against another one to be -1. The matrix is obviously symmetric. Flip everything up. And so this matrix has determinant. Of course, you know this off the top of your head. It's 2. Okay? So this determinant's non-zero. So in fact, the form is non-degenerate. And that means that has rank 3. And so what one deduces from all this stuff is that Bx shows up as a summand inside BSW with multiplicity. Well, so you have one guy in degree -2 showing up, paired with one guy in degree 2, and then 3 guys in degree 0. And this is exactly the computation that you showed was what should happen. Whereas in characteristic 2, everything is the same. The only difference is that the determinant is 0. So this form in characteristic 2 has rank 2, not rank 3. In characteristic 2, only 2 copies will show up here. E squared equals 0 minus 2 plus 2. And so things will be different. All the numbers showing up were ones. I should point out that there are more maps in degree 0 than just these. Okay? Because there's another map in degree 0, which is take this guy and multiply by any polynomial on the right. So this is a map of degree 0. So any linear polynomial. Sorry, f is linear. Okay? This must be in the kernel of the intersection. Okay? Because what does it pair against? It pairs against something of degree 0. Okay? So if I then pair this against something of degree 0, okay, then what happens is that really I'm pairing the thing of degree -2 against the thing of degree 0, and then multiplying by f on it. But a pairing of degree -2 with 0 gives me an endomorphism of x of degree -2, but there are none. Or they're all lower terms. Actually, yeah. They're all lower terms. Okay, so that means that this local intersection form has to vanish when you pair things whose degrees add up negative. Like, really, what you can do is you can have the k here next with an L there and have them add up to some number. And if this number is negative, you get 0. And if the number is positive, you get actually a polynomial appearance. Okay, so you can get an intersection, a local intersection form valued in R instead of valued in R as in the polynomial ring, as with R the real numbers. Okay? And then that intersection form is right R linear. Okay? But the point is, if you're doing the one valued in the real numbers, then anything in the image of the action of polynomials on the right is 0, is in the kernel of this form. This cannot possibly pair against it. So that is. Yes. That's exactly right. That's exactly right. There are endomorphisms of, x underline, which of negative degree, but they have, but they are all lower.